Hi, welcome to the Calculus 1 lecture series. We are in the unit number 2, talk about the derivatives. This is our lecture number 16. We talk about the related rates. This is our second video. For the first video about the related rates, and we introduced some very basic procedure, the steps to solve the related rates. And we did a couple examples in the related rate. So for this video, we are going to continue to work on some related rate problems. And those problems is a little bit more complicated than the first video's problem, but they basically follow the same way. Okay, so now let's go ahead and go to our lecture notes here. Okay, so for the previous video, we talked about there were 5 steps when we try to do the related rates, right? So in order to review these 5 steps, so let's take a look at the problem number 3, and then let's use the problem number 3 as a good review tools to see what we did in the first video. Okay, so the problem number 3, they tell you an observer is 300 meters from the launcher pad of a rocket. Watch it ascending vertically at 60 meters per second. Find the rate of the change of the distance between the rocket and the observer when the rocket is 400 meters high. Okay, so remember the step number 1 we defined in the first video is we say, hey, when we do the related rate problems, what do we do here? We said we're going to draw a picture and so help us to understand. Okay, so I have a person standing here, okay, so who is like, this is the launch pad, right? So this is the launch pad of the rocket. So this person is what? It's 300 meters, okay? And then the rocket launched vertically, so like this way here, okay? So let's see here. So this is our launcher. This is our rocket, right? Okay, looks pretty good. Okay, so now so it ascend, it's ascending, that means go up in the 60 meters per second here. And now I want to find the distance, the rate of the change here. I want to find the rate of change, the distance between the person and the rocket, okay, when the rocket is 400 meters high. Okay, so that's all. So we want to find when this one is 400 meters high. Okay, so now the step number 2 is here. We say let's list all the known and unknown variables here. Okay, and so we can say let x is equal to the distance here. So I will say, okay, I'm going to say that this is the x. The x is the distance, okay, between the rocket, right? So this is the distance and between the rocket and the launch pad, okay? And then we also said another variables here. This is y here, right? So let's say the y is the what? Y is the distance between the observer and the rocket. All right, and we also put all the known and unknown variables there, right? So that we say the dx dt, so the how fast this one we know, right? So dx dt is what is 60 meters per second. And then we want to find how fast the rate of change, the distance. So we want to find the dy dt. That is what we want to find here, right? Okay, so after this, then we said step number 3. So remember I said step number 3 typically is the hardest step. We want to find, connect all these variables. And in fact, this one is not too bad, right? So we said this is a right triangle. We love right triangles. So right triangles here, the x and the y and the 300 meters. So what in here, we have a Pythagorean series, right? So we said y square is equal to the 300 square plus x squared, okay? And then the step number 4, after we find this number 3 here, like we said, the number 3 is the most keys, right? If you find it, then the number 4 will be pretty easy. You just take the derivative respect to t on both sides. So in here, you will have to take the derivative of y, you will get a 2y, and then you will have the dy what? You will have the dy dt's here, right? And then the same way for the right-hand side, you can do that. So 300 is a constant. So what in here, you can have a tx, and then by the chain rule, so this is dx dt here. So remember, right, we want to find, we want to find the dy dt's, right? So then we know the dy dt is what we're going to looking for. Will just be the 2x, this is 2y dx dt. All right, so 2 we can cancel here. Okay, so now after we do that, then let's take a look at the number 5. Let's try to find it, right? So the dx dt, so this one's here. This is, we know, this is 60 meters per second. Now we need to know what is x's and y's here, right? So it said that when they want to find the rate of the change when the rocket is 400 meters high. So what's that mean? That means my x here is what? Is 400 meters high. And now I'm going to find the y's here. All right. So I'm going to find the y's here. So I know that x is 400 meters high. When x is 400, how much, what is the distance for y? So I know the y square is equal to the 300 square plus 400 square. And then I can find out the y is equal to what? Is equal to the 500 here. Now I can just substitute back to this ones here. So this is dy dt is equal to the x equal to 400, y is to 500, dx dt is what? Is 60, right? So now you use your calculator, you will find that this is the 48 meters per second here. Okay, so this one still is a kind of a very, very basic kind, because the right triangle is easy, right? So the Pythagorean theorem basically can find the equation in the step number 3 is pretty easy. Okay, let's take a look at the number 4 here. Okay, the number 4 is a little bit complicated. It's not too bad as long as we can draw the picture and find the relations here. Okay, so it says a light is the top of the 12 feet vertical pole. So in here, this is a pole here. This is a fixed number, is 12 feet. I have a light here. Okay, a 6 feet tall woman walks away from the pole base at 4 feet per second. All right, how fast is the angle between made by the woman's head and the light and the pole base when the walker? So how fast when the pole base changes 2 seconds after she started walking? Okay, so I have a lady here. Okay, so you say, okay, I have ladies here, and this lady is 6 feet tall. All right, and so this lady is walking, and then this light is shining on this lady's here. Okay, so now in here, let's try to put here. So this is 12, right? So this lady is here, the tallest lady is here. Let's kind of put here, the lady is what? Lady is 6 feet. All right, and what we are looking for here, we are looking for these angles, right? So when we want to see when the lady walk, and then how fast this angle going to change here. All right, so I guess that's all the information we have. We draw the pictures, right? So this is our number 1 step here. Now let's take a look at number 2. They said list all the known and unknown variables here. So we said theta is the angles, right? Okay, so now I will say here, let's see here, the x is the base. So I will say x is the distance. Okay, so the x is the distance between the pole space and what? And the woman, right? Okay, and then I can have another ones here. So this one I called this is y here, right? So I will say y. What is the y here? Y is the distance, right? Be the distance from the woman, right, to the tip of her shadow. Okay, so this is my x and the y's here. Okay, I guess that's all the information I have. So if this is x and y, then I know from here to here is what? From here to here is x plus y here, okay? Now the toughest ones here, let's think about the number 3's here. The number 3's here is, let's say, hey, let's try to find this relation. Okay, hold on, we have one more thing we did not know. So the woman walk away from the base. So that means it's dx dt is equal to what? Is equal to 4, right? So this is what we know. And then we want to see how fast the angle changes. So the d theta dt, this is what we need to find, right? Okay, so now let's try to put this, all this information together here. Okay, so when you do this type of problem, so take a look here, right? So really you have a little triangles here. Okay, and then you have the big triangles here, right? So you have a big triangles here, right? So the green ones here, and in fact, I don't have this problem did not use the information about y, so I want to replace the y out. Okay, so if you take a look at this big triangle and the small triangle, so I know by the similar triangles. Okay, so x plus y, okay, so the x plus y over 12, this is to my green triangles, right? X plus y to the 12 here. And try to color coding that. So x plus y is this side. So you compare to the small triangle, what is that? Is y. And what is the 12 here compared to the yellow? Is 6, right? So like if you see, this is how do I kind of color coding that? So by the similar triangles here, that's why I can get these ratios here. After you get this ratio, then you can solve it. So you say the 6x, you do a cross product, 6x plus 6y is equal to what? Is equal to 12y here. All right. So then that means 6x equal to 6y here. So that's why you say x equal to what? X equal to y here. Okay. So now if x equal to y, so I know that x plus y is equal to what? Is equal to 2x here. Okay. So now let me transfer this triangle, this green triangle to here. Okay. Okay, so be careful. This is the green triangle. We just solved it, right? Okay, so in here, this is x plus y. So what is this here? This is 2x. And what is here? This is 12, right? And this is our angle theta. So I want to find a relation. So do I find it? Oh, yes. So what is the relation? I have a tangent theta is equal to the opposite over adjacent. So it's 2x over 12, right? So then I will have x over 6. So I will have the what? 6 tangent theta is equal to what? Is equal to x here. Now we got it, right? So we said, okay, so this is the number 3. So this one is a little bit difficult than another one, but we find it, right? So we find it by using the similar triangle. That's one of the function about the related rate. So you can, try to find the number 3 is the most challenging ones, but it's also the fun one. Okay, now after that, you can just take the derivative of both sides. So if I take the derivative of both sides, so this will be the 6 tangent derivative. We know it's a secant square theta, right? And now this is what? Dx dt, right? Okay. So now let's take a look here. So we know, okay, so the 6, okay, so now in here, let's take a look here, right? So let's back to these triangles here, okay? And we want to find the d theta dt's, right? So this is my angle theta, right? Okay, so this is 12 here. So I need to find what is here. Okay, so we know the dx dt is 4, right? Because they move away from so this is given. So this is 4, is here. Okay, but now I need to know, so the d theta dt, okay, so here, let's see here. So here I need to be careful here. I forgot to take the derivative. I need to have a chain rule, right? So that's why if you're not careful, you will forget about that. So this is a 6 secant square theta d theta dt. Okay, so the d theta dt is equal to 4 over what? 4 over 6 and the secant squares, right? Or is 4 over 6 cosine square theta. Okay, so now let's take a look at cosine square thetas here, right? So in here we know, okay, so in here, this is 12, right? This is after the 2 seconds here, okay? So after the 2 seconds, how, because it's travel at the rate of 4 feet per second, right? So after 2 seconds, how much I travels here? I travel the 8 feet. Am I right? Okay, so then the 8 feet is after 2 seconds, I travel the 8 feet, but I know these things here, this one, is how many x here is 2x, right? So I know what is here, this is 16. Then by the Pythagorean theory, then what is this ones here? This will be what? This will be 400s, right? So it will be 20s here. Am I right? Okay, so this will be 400. So this will be 20. Okay, so now by the cosine square theta, I finally can get it. So this is 4, 6. The cosine is what? Adjacent. So it's 144 square over 400. Correct? So now if you calculate that, this will be 0.24 radians per second here. Okay, so in here, be careful, right? So the 2 seconds, right? Because I know every seconds I travel 4 feet, right? The speed every seconds I change to 4 feet. So 2 seconds I travel 8 feet here, right? So 2 seconds I travel 8 feet. But then here, this is 2x, right? So that is why, so this is, that's why, the 2x here, that means the total distance here is what is 16 here, okay? So this one is a little bit harder and others, but it's not too bad. So first you need to recognize it, try to use the similar triangles relations, right? Okay, now let's take a look at another one, the last problem for this practice. So like number 5 is here, they say a 10 centimeter thick nail wheel is initially 90 centimeter in diameter and is welding away at 55 centimeter cube per hour. Now, how fast is the diameter change after 220 hours? After 20 hours here, okay? So let's see here. All right, so first things, let's try to do, I hope I can do a good job. Okay, so this is the, okay. Haha, this is the, so this is the mill and okay, so the in here, then they say it's a 10 centimeters thick. So I know this one here is a 10 centimeters thick, right? And initially, this diameters here, initially, this is what? This is 90 centimeter, right? Okay, then they wear off at 55 centimeter cube per hours here. Okay, so now after we did that, then the number 2 see here, we want to find all the known and unknown. Okay, so we know, okay, so that's the V. I think the V is the volume, that's right? So let V be the volume of this mill. And X here, let's be the diameter of this one. Okay, so here, this one's here. So this is the diameter, right? So we say it's X here, okay? And then the known things here is said here, the mill, okay, is welding away at 55 centimeter per hour, centimeter cube per hour. So that means what is given here? The dV what? dt, right? So the dV dt here is 55 centimeter cube. That means it's negative 55. The reason why I put it as a negative is because it's, they say, is welding away. That means it's getting smaller and smaller, right? So it's a negative here. Okay, now I want to see how fast is the diameter. So that means I said dx dt, this is what we need to find here, okay? So for these ones here, the equation number 3 is not too difficult to, to do it because we know this, this is really is just cylinders, right? So the cylinders here, we said the volume is what? The cylinder of the volume is a pi r square and then times the height, correct? Okay, so pi r square. So, okay, so the height is 10, right? So the, this one here is 10 here. So this will be 10 times pi r, so pi, then r is what? X over 2, right? So x is diameter, so pi r square, so it's x over 2 square. So well, if you simplify, so 2 and 2, so it's 4, so this is 2.5 pi x squared. Okay, now after number 3, number 4 is easy. Number 4 is, hey, take the derivative of both sides. Okay, so I say dv dt is equal to 5 pi x dx dt. That's right. Okay, 5 pi x dx dt. Okay, so now let's take a look here. So the volumes here, right? So in here, let's say the volumes, like for every hour, they wear off at negative 55. So that means after 20 hours, right? So the material worn off, how much? So worn off is 55 times 20, right? So after the 20 hours, the material worn off the 1100 centimeter cubes here. Okay, so that means the original. So the original material, that means before it start is a V is a what? It's a pi r squares, right? So it's a pi r, r is what? So it's a pi r square, r times, so pi times 10 times 90 over 2 to the square, right? Okay, so this was the original. Okay, so this ones here is like so this is my original, and then now here. Okay, so now how much is left? How much is left? So after 20 hours, so it will be 10 to the pi 90 over 2, so it's 45 square minus this how much, right? This is how much worn off after 20 hours. So it's so what has left? What left us here is about 62517.25 centimeter cube. So this is how much left, right, after 20 hours. Okay, now I can find it. So I say, okay, so now in here, that's the volumes, right? So I know the volumes here is 62517.25 is equal to what? 2.5 pi x squared, right? From here, right? From here. Okay, so now I can find what is here. I can find, so I can find x here is approximately to 89.2 centimeters here, right? So that means the x here after 20 hours, now the x is dropped to the 89.2 centimeter. So finally, right? So the dx dt, all right? So the dx dt will be equal to, let's try to put it into the formula. So how do we try to do here? Okay, so we want to find the dx dt. So dv dt is negative 55 is equal to 5 times pi times x 89.2 times dx dt. All right, so the dx dt, if you plug in here, we can get this negative 0.039 centimeter per hour. Okay, so this one is a little complicated. Even the formula number 3 is kind of easy, but then you need to know because they're looking for is the rate of the, so the here, right? So, you know, this is the one we want to looking for is the dx dt's, right? So we want to look for is dx dt, and so why here they kind of okay, yeah, dx dt. All right, so we want to find is dx dt. Okay, so this is dx dt, and then the reason why the extra step is because we need to find this x's here. So that's why you need to see how much it worn off after 20 hours. This is much. And this is the original materials, right? So it's a pi times 10 times 90 over 2. So this is the original. Then the original minus how much, this is how much left, right? Then you plug back in to find the x. Then after you find the x, you plug back into the number 4 here to find the dx dt's here. All right, that's it for the related rate. And like I say, it's a very interesting sections. And, you know, the problem sometimes very challenging and you need to know, like I said, most challenge one is probably the step number 3, try to find it, and then try to find all the known and unknown variable and then substitute. Okay, that's it. All right. And I hope you enjoyed this application about the derivative is related rate. Okay, so looking forward to talk to you on our next topics here. Okay, bye.